Today we have the pleasure of hosting Esperanza Lopez. So Esperanza, she's a researcher in Madrid, in the IFT, the Theoretical Physics Institute of CSIC, and Autónoma University in Madrid. So Esperanza, she made her PhD in Madrid, actually in the CSIC, but after that she went for a long period of research in other institutions. So she went to Santa Barbara, she was also in Vienna, she was also in the CERN institution, she was also in Potsdam, right? And then she came back to Madrid, to the Institute of Theoretical Physics, in which she's working now. So her background is mostly on, let's say, very theoretical physics, I would say, right? But in the last years, she's also moving into quantum information, as many other people, I think, in the field, in her field is doing. So we are very happy to have you here, Esperanza, and welcome to the IPC. Okay.
Okay, so thank you for the nice introduction and for the invitation here. I'm really happy to be here in the IPC. So I'm going to present a research program that is already ongoing for several years, and it consists in trying to prepare integrable eigenstates of integrable systems on a quantum computer. So, so maybe, I don't know, if any question, if at some point is like too technical or whatever, just please ask. I mean, we are not many, so. Okay, so.
We need to press it once. Not working.
Now it's on the Zoom channel. You should touch it, the mouse on the screen.
I cannot scroll either with my.
Will you meet, are you?
No, yeah, touch the screen.
Sorry?
Click on the screen now.
Click in the list.
Yeah. Just clicking on the screen. Yes. I was moving with the sorry. I'm forgoing about. Now it's sorry.
Okay.
So I will start with the motivation of why we are interested in this problem. So, well, as we all know, quantum computers are experiencing a very fast development. They are moving from the NISQ era, where only it was possible to do error mitigation, to the first stages of quantum error correction. And maybe we can expect that in the not so far term, we could have applications that give us quantum advantage in useful problems. So one of the realms where maybe we can expect quantum advantage is the study of quantum many-body physics. So there are many problems that can be treated, but the one in which we are going to focus is that of preparing interesting entangled states, so in particular, eigenstates of interesting many-body systems. So why this is interesting? First, because if we manage to prepare these eigenstates in a quantum computer, so we could have access to the non-local properties that are very difficult to get by any other means, even by tensor networks, and we could just obtain them just by measuring. So that will be, of course, this is of course a great interest. So also being able to prepare known states will help up in benchmarking these quantum prototypes, and also the entangled states can be interesting as initialization states for other algorithms. That can be time evolution, or can be even for adiabatic algorithms, etc. So now, although quantum computation is universal, implementing an arbitrary unitary in general requires exponential resources. So when we talk about quantum computation, it's very important to know if the tasks we want to implement can be implemented efficiently. And this means that it only requires polynomial resources in the size of the problem that we want to pose. So characterizing the quantum computational complexity of a given task is essential and is also not an easy problem. So in particular, the question really that we want to address is what systems admit an efficient quantum circuits to prepare their eigenstates. So it's known that efficient circuits exist for free fermions, but this is not so interesting because free fermions are also classically simulable. So the next step in complexity, instead of going to a general system, is to address integrable models. So integrable models have been instrumental in understanding many-body physics. They have constrained but very rich dynamics. The constraint comes from the fact that they have a complete set of conserved quantities. So it looks an interesting first stage to address this problem. So actually, the question that, at least for me, is the most interesting is what is the leap in complexity in going from free to integrable at the level of using a quantum computer. So, and then there are different approaches that can be used, but what we are going to be interested is to see if the well-known integrable structures, so integrable systems, they have a very rich mathematical structures that is very well understood, and to see if this knowledge can help us in design efficient quantum circuits. So now, in front of this problem of preparing some particular state or eigenstates in this case, there are different levels of things we can ask. For example, we can be interested only in preparing the ground state, or we can be interested in preparing the state within some approximation. So the thing we want to do is to search for algorithms that are capable of preparing arbitrary eigenstates, because the integrable structure gives us a way to construct eigenstates, that is the famous Bethe Ansatz that I will introduce now, that in principle can address any eigenstate. So what we want is to see if we can translate that structure into a quantum circuit. And also, we don't want to use an approximation, but we want to, in principle, I mean, of course, then the implementation will have its error. But the algorithm, we want that, in principle, should be able to prepare the states exactly. Because we want really to see if the mathematical structure has a translation into a quantum circuit. So the problem of preparing eigenstates of integrable system is something that has attracted quite some attention in the last year. So we added to the different approaches that have been followed. So the outline of the talk, it will be first an introduction to the Bethe Ansatz. Then I will present how to go from the Bethe Ansatz to a quantum circuit. And then I will mention an algebraic structure involved in all the developments we do that is something very deeply ingrained in the theory of integrable systems that goes under the name of F-bases, but I will talk about that. And then I will show that how we get efficient circuits from free fermions. In the general case, we still don't have an answer. Actually, I thought we already will have some results, and the abstract I sent, it was based on the hope that we already had that results, but we are in the process still of doing so. I will say something about the general cases. So then, since we don't have yet a clear answer for an interacting integrable system, so in general, so we will see that there is a simple interacting chain that is sort of a rigid rod deformation of the spin 1/2 X6Z model that really admits exact circuits for preparing all eigenstates, and exact and efficient. And then I will I give just a simple overview of what are the circuits, and then we did some simulations of that circuits to see if we could prepare them in some of the quantum computers we have now. So that will be the outline of the talk. So What integrable systems I'm going to be concerned? So they are integrable spin chains that I'm going to consider closed spin chains. In each of the sides, it leaves a spin 1/2. It will have n sides. And in addition, I ask for the dynamics to preserve, to have a U1 symmetry, such that the excitations of this of the system are spin waves that are called magnums. So the paradigmatic example of this situation is the X6Z Heisenberg chain that it has this Hamiltonian. It has here an anisotropy parameter such that the SU2 symmetry of the usual Heisenberg chain is reduced just to U1. So at the more physical level, integrability in this context, what it means is that the scattering is always two-body reducible. Even if we have several parties interacting, the interaction can be reduced to two-body processes. And also in one dimension, this means that the momenta don't change in the scattering process, but they just get redistributed. So under this condition, there is an answer for constructing the eigenstates that it was formulated by Bethe a lot of years ago. I don't remember exactly, maybe in the 30s, I'm not sure. And it goes under the name of the Bethe Ansatz. So I'm going to just present it in what consists the Bethe Ansatz, that in this formulation, because I will present a more algebraic formulation, sometimes it's also called coordinate Bethe Ansatz. So the Bethe Ansatz consists in making an ansatz for the eigenstates that is a plane wave superposition whose coefficients are product of two-body scattering amplitudes. So it's just a superposition on plane waves, and the coefficients of the superposition, we impose that they have this two-body factorization. So, for example, the scattering amplitude for the X6Z has this form in terms of the momenta of the magnums. So the two magnum wave functions, it has these expressions. So here are the plane wave factors, and these are the scattering amplitudes. And here the N1 and 2 just means the positions where the spin one flips they live. So in the general case, instead of being that, these coefficients will be products of these scattering amplitudes. So this is the Bethe Ansatz for the eigenstate. So in order that this is really represent an eigenstate, one in addition has to impose the so-called Bethe equations on the momenta. And what the Bethe equations mean is that they impose the periodicity of this wave function such that you can consider that it lives on a cycle, on a closed chain. Because in principle, this is an answer for that here the momenta, they are free. So in order that this represents eigenstates, one has to impose the Bethe equations. So this is a very physically intuitive way of constructing the eigenstate, or making an answer for the eigenstate, but it turns out that there is a much more algebraic way of constructing the eigenstates, and this formulation goes under the name of algebraic Bethe Ansatz. So in the algebraic Bethe Ansatz, the main object is an R matrix that is a four-leg tensor, actually, that leads to a systematic derivation of the complete set of conserved charges. So that's the interest of this formulation, that gives you a systematic access to the conserved charges. And this R matrix has 4 legs, and 2 of them, they live in the physical space, that in our case, in our index is just a spin 1/2, and then it has another 2 legs in an auxiliary space that is going to be also an spin 1/2 space. So the R matrix satisfies the celebrated Jan-Buster equations that has this form. And in terms of thinking that the scattering is two-body factorizable, this just means that no matter in what way we do the factorization, we always get the same answer. That is a physical requirement to make sense of the two-body factorization. Okay, and then of course, the R matrix has a spectral parameter that can be interpreted as the momentum of the magnons that we want to construct. No? We want to construct eigenfunctions that contain a certain number of magnons. Yes?
What is the meaning of charges here? Positive and negative charges? Or maybe I lost.
Sorry?
What is the meaning of charges?
I mean, they are conserved charges that commute with the Hamiltonian. And in an integrable system, you have as many as degrees of freedom. And in addition, these charges, they are quasi-local. So, I mean, when you, the first ones, they are very local, then they grow the range of interaction. And there is a way, using the R matrix, you can construct this type of object that if you here don't put a 1 and a 0, but you let open, this is called the monodromy matrix. And in terms of that construction, you can systematically derive all the conserved charges. Okay, so and in terms of this object, you can also systematically construct the Bethe states. And the way of doing in this context is you consider a row of this R matrix. Each one will depend on a parameter P that is going to be interpreted as the momentum of the magnon we create. Here you introduce a 1, you impose here a 0, and since we are considering systems that have U1 conservation, this forces this 1 to go out here, and this creates the one magnon wave function. So this thing, and these are end sides, the end sides of the chain that we are considering. And this thing I have shadowed here in blue is what is called is a magnon creation operator. This part here. This is more or less clear? Okay. So actually this structure here is the same as a tensor network, the simplest tensor network ansatz for approximating one-dimensional quantum many-body states. That is they are called matrix product states. So this approximation is based in the following idea. So if we have a wave function on a chain on n sides, so in principle, the coefficient of that wave function, they will be a complicated tensor with n legs. And of course, this we cannot address because the number of this coefficient, it grows exponentially with n. But then the idea is that for some particular states, in particular for the ground state and the low-lying states, one can do an approximation, a reasonable approximation to this complicated tensor as a product of smaller tensors. So this essentially, if this instead of matrices, these are matrices that have one index in the physical space here, and they have two indices in an additional auxiliary space whose dimension we have to also determine variationally. So if the dimension will be 1, then we will just have a product state. And that will have no entanglement between the different physical spins. So in the moment we increase the dimension of this space, we are able to represent more and more entanglement. So if the state we want to represent doesn't have much entanglement, so this type of approximation is very useful. And as you see here, instead of the number of parameters to determine this ansatz growing exponentially with the number of sides, here it just grows linearly with this number of sides. And then, of course, the question is that if we can find a low dimension, if a low dimension for this auxiliary space is enough for representing, if it's like that, then it's efficient. And then you see comparing here that the auxiliary space in the algebraic Bethe Ansatz construction, it looks very much like the auxiliary space of the NPS construction. So now, if we want to construct a and n magnum states, then we just pile up rows of these R, each of them representing a magnum creation operator. We apply it in the vacuum, and each of them will create a magnum. And in the end here, we put here the M1s, and we will obtain the wave function of an state that contains n magnums. And now we can still interpret this network as an MPS if we look instead of to the rows, to the columns. So we can see this column as an MPS tensor with 3 legs, the physical one and the auxiliary ones that now will be composed by all these auxiliary spaces. And I mean, this I have keep here dotted because it will be useful to have into account that actually this came from having here an entry 0. And then the auxiliary space in this case, since we have here M auxiliary spaces, goes, and each of them is a spin 1/2, it grows like 2 to the n. So this construction is formally like an MPS, but it requires a very large bond dimension, auxiliary space. And this is the reason for that is that this is not an approximation to the state, but it gives the exact construction. So we need, I mean, a very large bond dimension to represent the exact construction. So in this paper, they try, based on this analogy, to search for some truncation, efficient truncation on this auxiliary space to that it was giving a good approximation, but they didn't succeed. And we will follow a different approach. But this it will be important to keep in mind this analogy with matrix product states.
Can I ask a question?
Sure.
I'm a little bit confused about you said at the beginning you have periodic boundary conditions.
Yes.
Usually in MPS you connect the legs.
Yeah, that's true. I mean, this is why I was saying here that in principle the answer doesn't you can formulate it for any momenta. So periodicity comes from imposing additionally the Bethe equations on that momenta. So the circuits we are going to have, they construct of cell, let's call those with generic momenta of cell Bethe states. So the Bethe equations, they will have to be imposed with some other method.
So the MPS itself is not periodic. It's not a
No. The MPS state, no. But and neither this. Only for some particular values of the momenta is. But this way, through the algebraic Bethe answer of constructing the Bethe states, connects very naturally with the MPS formulation. So, and then we can use all the intuition of MPS to reason over this problem. So now, if we want to do, our aim is to construct a circuit that is able to prepare these eigenstates. So we can do a gate-like interpretation of the MPS tensor as follows here. This sort of Gauss 0 can be written here as a input 0, and then these entry auxiliary space labels, they will go here, and in the end we have here the physical leg and the other auxiliary legs. So like that we can interpret this MPS tensor in a gate-like way. But of course, this is not in general a gate, because for that, this will have to be unitary, and in general, it's not unitary. So our problem is that we need to transform this into something unitary. But it's a well result of the MPS construction that if you introduce some, in principle, arbitrary functions in the matrices in the auxiliary space, you can transform this tensor into an isometry. So let's say into a unitary. And once we do that, and this is always possible, then you can interpret it really as the gate of a quantum circuit. So, but the price to pay is that while this gate-like tensor derived from the algebraic Bethe answer has this decomposition in terms of two-body processes, this one is a complicated n+1 qubit gate if we want to generate an n-qubit state. So what we have is that we can write it in this form. These are the input ones in the auxiliary space, and this is the projection into zero afterwards. And this shaded region is the flow of the auxiliary indices. So we can reinterpret this. I mean, we can transform this into this circuit. So what happens is that this will be a probabilistic circuit, because we will have, I mean, we will need m plus m qubits, and in the end, we need to project into zero some of the output qubits. And projected into zero, this is very costly. It has a very high short cost, so it will grow exponentially with m. So it's not very practical. But actually, it's possible to just eliminate this extra qubit. And the reason is that it lies in the Smith decomposition. So the Smith decomposition says that whenever we have a system and we have a considerable partition of this system, this state can be written in this form, in a product of, let's say, orthonormal states of one part, the A part, and other on the B part. So the number of those is bounded by the smaller dimension, the dimension of the smaller subsystem. So if we start here in the end of our circuit here, so actually, and we partition between all this part and this, so one of the sides A will be just a single spin. So this means that actually this leg can only have bond dimension 2. I mean, apparently here we can write more, but essentially it has, like that, I mean, it will be increasing just by a factor of 2 until we reach the maximum size of 2 to the n. So this means that actually all these tensors, they can be without losing any information, they can be reduced, and in the end we can construct a deterministic circuit of this form. And the whole construction, this will be exact, so we will have our deterministic circuit. So here I have remarked that really this circuit is able to construct of cell Bethe states, so states of this form for any momentum. Okay, now the problem is that in order to get our unitaries, we have to find these matrices here. And starting from this algebraic Bethe Ansatz structure, we were only able to obtain them numerically. And of course, our intention is to try to understand this problem at a more mathematical level, analytically. So starting with the algebraic Bethe Ansatz, we didn't succeed in doing it. So then actually, it turns out that it's more reasonable, right, to look at, since the Bethe wave functions are more intuitively described by the coordinate Bethe Ansatz, the superposition of plane waves, instead of by the algebraic Bethe Ansatz that has other advantages, for example, obtaining these conserved charges, as I have said before. But, and then in addition, even if the coordinate Bethe Ansatz and the algebraic Bethe Ansatz construct the same eigenstates or the same states, there are involved normalization factors that relate one and the other construction. They are simpler, those of the coordinate Bethe Ansatz, are very involved in the case of the algebraic Bethe Ansatz. So it looks probably more natural to start on the coordinate Bethe Ansatz. And it turns out that the Bethe Ansatz also admits an MPS interpretation. This is a much less known result. And actually, we were not so much aware of it when we started it, but it was formulated in this paper first, and it was also a very abstract construction. And actually, after some years, it was shown for the case of the XX how to go to that construction starting from the algebraic Bethe Ansatz. But let's say that these were not such known references as some of them at that point we even didn't know. So somehow we rediscovered the MPS based on the coordinate Bethe Ansatz. And this has a simpler structure, and it turns out that it allows to obtain these matrices, these matrices that now are different from these others since the starting point is different. So the ones that bring this MPS tensor into a unitary, they can be obtained analytically. So I'm going to just explain how it goes. So first, let's see a little bit how the two MPS construction of the coordinate Bethe Ansatz versus the algebraic Bethe Ansatz. So for the algebraic Bethe Ansatz, I have seen that we have seen that this tensor, it can be decomposed as the product of this R matrix. So it has this sort of two-body this two-body decomposition. So in the coordinate Bethe Ansatz, the structure that we got sort of independently, because we were not aware so much of that reference, it was that it could be obtained using very simple diagrammatic rules. And the first is if the physical output qubit is in 0, so it just sort of acts, shifts the ones by one left, and every time it shifts, it gets a momentum factor. And if the physical index here outputs a 1, the situation is more complicated. And if we have lines, well, this goes under some diagrammatic rules, no matter, I don't enter here, but the fact is that we have lines, Magnum lines, these ones, that they cross, they acquire some factors that are essentially the scattering amplitudes. A -1 because these magnums for the XZ that behaves as fermions, and also the scattering amplitudes themselves, characteristics of the XZ. So somehow the CBR managed not to have a trivial two-body gate decomposition, but it has, in essence, satisfied the two-body factorization, because the only thing that enters are these two-body amplitudes. So if you have more crossings, then you will have products of these two-body. And then somehow this structure that is not very complicated, but still doesn't have this trivial two-body decomposition, is able to absorb already some of the complication. So now this is the additional element that, because it was not clear how to go from the CBR to the ABR systematically, or what was the structure involved in relating these two MPS structures. So it turns out that the structure, the integrable structure involved is something that is called F-bases, that seem to be also something very deep in the theory of integrability. And the fact is the following. So in some cases, and in particular for the XZ, the R matrix that is not unitary but in general satisfy what is called braiding unitarity. And it means somehow that you braid with the R matrix and you braid the second time, you get the identity. And when this is satisfied, sort of the R matrix can be undone in terms of two additional matrices that are called F in the literature. So what it means is that if we apply this to the Yang-Buster equation, it means that the Yang-Buster equation tells us this. But if we use the R matrix, we can write it in this other form. So somehow what it means is that the non-commutativity of the R matrix, because applying first R1 and then R2 with different momenta associated to indices 1 and 2, is not the same of first acting with 2 and then with 1. But if we combine that with the change of bases in the auxiliary space, it turns out that the result is the same. So somehow this F basis is a change of basis that undoes the non-commutativity of the non-triviality of the R matrix. And this can be generalized. So there exists also this Yang-Buster equation. They can be generalized to the case of these R matrix networks that construct the eigenstates, and is that if we permute the rows, we can relate the rows in an initial order and in a permuted order with a certain generalized R matrix that is product of R matrices. So it's a generalization of this relation. And when the R matrix satisfies this braiding unitarity that I have mentioned before, also the F matrix generalizes, and there is a change of bases in the auxiliary space that makes this multiplication of rows of R matrix in the invariant under permutation, explicitly invariant under permutation. So now we can use this change of basis that lives only in the cellular space. We can apply it to each of to each of these columns. We could insert between each of them f and f to the -1. And then it turns out that this is precisely what converts the MPS tensor associated to the algebraic Bethe answer into the MPS tensor associated to the coordinate Bethe answer, up to some local transformations, that are local in these legs. So this was a result that maybe it was a bit hinted in the literature, but it was not really stated before. And I believe that is an interesting statement for the theory of the integrable systems itself. And this property of being invariant under permutation, it can be seen that implies the following property for our circuit when we base it in this the coordinate Bethe answer tensor, is that in this case, whenever we input here, we don't only need to input just 1, 1, 1 to get here a Bethe state. Whatever we input here, we always output a Bethe state. So this property is not true if we use this other tensor. But if we use the one of the coordinate Bethe answer, whatever configuration we put here of 0s and 1, the output is a Bethe state. So let's say if we put 3 ones, so we will have a Bethe state on the number of sites we consider here, let's say k, with the momenta that we have associated to each of the legs. Recall that here, in this MPS, sort of each leg has associated a particular momenta. Well, it's a bit fast to explain it. And then if we will input here a 1, 0, 1, we will get a 2 Magnon state with momenta P1 and P3. And if we get 0, 0, 1, we have a 1 Magnon state with momenta P3. So this means that actually these matrices here, their role is to change to an orthonormal basis in the space of Bethe wave functions on k sites. And since we know the form of these wave functions, we can get this explicitly these matrices, for example, using the Gram-Schmidt processes. And in this way, we could have analytical expressions, and we could get all the all the elements of these Bethe circuits analytically. Okay, so the resume will be the following. So we got this Bethe circuit, the circuits for preparing off-cell Bethe wave function. We were able to obtain analytical expressions for the multi-qubit quantum gates. In addition, we got this result that I think is interesting in the theory of integrable models, that is the algebraic structure behind the algebraic Bethe answer is the R matrix, but that behind the coordinate Bethe answers is this F basis. And now all this construction, once seen in these languages, it can be seen that it generalized to open chains and also to the inhomogeneous Bethe answers. So it can, this more abstract view, it also helps to generalize. So now, of course, the question is, what is the computational complexity of implementing these multi-qubit gates? So now we have them, and we have them analytically. So, but the big question to know if this is actually, this gives us an efficient circuit, is how many elementary unitaries, 1 and 2 qubit unitaries, are required to decompose each of these gates. So if the circuit is efficient, we need that the number of elementary gates is polynomial in N and in M. So actually, it turns out that for free fermions, these complicated multi-qubit gates, they can also be decomposed in 2-body unitaries. The construction is a little bit more complicated than in the case of the R matrix, because in the case of the product of, of R matrices, each R matrix was depending only on one of the Magnon momenta. While here, for example, this last gate depends on all of the Magnon momenta. But still, these are, it can be seen that the decomposition is not only efficient, but really very efficient for the case of free fermion. And actually, this matches the efficiency of other algorithms that have been proposed also for constructing free fermions. But as I have said, this is not so interesting because the type of gates that are implied that are called match gates are classically simulable. But now we managed to have a framework in which we treat in the same way the free and the interactive. So the hope is that this helps to give the jump towards the interacting integrable chain. And then, given this fact, the natural thing is or the first thing that comes to the mind is to try a multi-layer answer for this gate. Before I was calling P, but now I called you because of a mistake, but this what I was calling P before. So we can try several layers of this two-qubit gates, where now will not be match gates, but something slightly more general. And then it turns out that if we were trying to reproduce each of these gates we got before, actually here this will be a P and also here a P. Okay, if we try to reproduce this construction that we got out of the Gram-Schmidt process, and so it turns out that the number of layers that we need to use grows exponentially with the number of magnons. So it's not efficient. But this is not the last word, because these are not the only, given once we have these matrices, any multiplication of this matrix by a unitary still will do the job. So the question is, if there is, instead of these matrices that we have derived from this Gram-Schmidt process of orthonormalization, there is a choice of B that makes efficient. And we have results that point towards the fact that yes, the answer is yes. If you choose appropriately this unitary, you can make that actually, if you have a gate for n magnons, you only need m layers. And that will be, of course, efficient. But at the moment, this is just numerical work that for some cases works better, for others slightly worse. But in particular for the Richardson-Godin model that is also integrable and very relevant to superconductivity, we get like 10 to the -8 fidelities or infidelities for states with 4, 5, and even up to 6 magnons. So, but still, I could not present yet these results. So, okay, I still have some, like a quarter of an hour? Or?
A bit less, if possible.
Okay, so, bueno, I could stop here, or I could just, let's see in a very summarizing way. So we found a case of an interacting integrable model where really we can get the circuit exactly. And the case goes under the name of the folded XXZ model, that it has this more complicated Hamiltonian, and is related to a strong anisotropy limit of the XXZ when delta goes to infinity. So the fact is that the dynamics of this model is very simple. It only allows for this type of transition. So it describes kinetically constrained hopping processes. And it has, in addition to the simple conserved charges are the number of qubits in one, of course, and the number of 0, 1, 1, 0 transitions. So the nice property of this model is that it has Hilbert space fragmentation. So it means that the Hilbert space breaks into exponentially many fragments that don't interact dynamically among themselves. And okay, so the spectrum of this model consists of magnons, like the C1s that move in a sea of zeros, and the dynamics is such that they cannot get close together. There is always of one side separation. There is a sort of contact repulsion, and then it has domain worlds that are like regions of several ones and several zeros. And Okay, it can be seen that each of the fragments, in the case of an open chain, it can be labeled by the position where the domain wall is most to the left and the magnons more to the right. And then it can be seen that the wave functions, the eigenfunctions of this model, they can be constructed out of the free fermion eigenfunctions by applying two unitaries that we have called U and D. The first one goes from just free fermions or free magnons into magnons that have this contact repulsion that I have mentioned. And the second unitary introduces the domain walls. So I will not go into the details of the circuit, but the circuit can be constructed. And it's complicated, but the depth of the circuit is not worse than n squared times d, that is the number of the domain walls. So it's efficient. And then here we consider the circuits for the simple cases of having just one magnon and two domain walls in 7 sites, let's say, in few sites. And for that, we only needed 11 qubits. And this is the particular circuit we got. I will not enter into it, but let me just briefly mention in what consisted the simulation. So we wanted to introduce like a realistic noise to evaluate if in the prototypes we have now, this will have a chance to run. And then we consider as the noise model, the polarization only for the gates that involve 2 qubits, with the polarization parameter around 10 to the minus 3, that is in the range of what now the chips have. And then we consider different qubit connectivities, because this is, of course, critical, because depending on the connectivity, maybe you have to introduce swaps and then you introduce more error. So we consider an all-to-all connectivity, characteristic of trapped ions and nearest neighbors, like characteristic of supercomputing qubits. In particular, we consider the square lattice that Google has. And then we decompose the gates in the circuit into the native gates that are C0 and rotations. And we run it in the simulation, and we apply some error mitigation strategy. And then we saw that the results are pretty promising. For example, for the energy, the noiseless result is 0.7. In the all-to-all connectivity, we got the raw results were 0.53, but after mitigation. So we got a reasonable estimation of the energy. And in the case of the nearest neighbor, we got a worse raw result, but after mitigation, it was also reasonable. And for this simpler observable, the results were pretty good. So in principle, these are candidates to be run in a computer nowadays, and expect that we can see something. So I finish just with this transparency. So the result, the circuits I have presented very just without entering into any detail, they can be generalized to hard-rod deformations, for example, of larger length. So, I mean, this is the idea of seeing that, I mean, we consider a very particular case, but it can be generalized to a certain family. So it will be hard-rod deformations of larger length. We can apply hard-rod deformations and domain wall insertions to eigenstates of other models using these circuits. For example, there are hard-rod deformations of the XXZ model without going to this strong anisotropy limit that I have mentioned. And also for Eigenstate, this seems to be relevant for these XPX models. And then another interest of this model is to study Hilbert space fragmentation on a quantum computer. For example, see the evolution and missing of fragments under a small perturbation. So, and then it can be also used for benchmarking, because there are some non-local observables are known exactly, and then it can be seen how the circuit really reproduces. So that will be all. Thank you.
So thank you very much, Esperanza, for this nice talk. So any questions, comments? I remind the people that are online that you can also use the chat to make any questions. Any questions, comments? If not, I have two very general questions. I mean, one is main one. So I'm not familiar with the formalism and the generation of eigenstates, but you are always using chains, right? Spin chains in order to model. Which other models could be also, let's say,
Well, I was using chains because it's the thing that maps more directly to the qubits of
okay, so that's the reason.
I mean, one could consider also instead of qubits, Q-treats, or I mean, not a spin 1/2, but a higher spin. And then going into continuous variables, I'm not sure, maybe something can be done also like for quantum field theories or so. I will not know. I don't know now how to, maybe it can be done, but I mean, this was the first trial, and the idea is really to see if there is this problem can be solved efficiently or not.
That's very useful. Okay, yeah, and the second very pragmatic question is also, let's say, as far as I understood, so what you have been doing is simulations, right? So you have to run this in a quantum computer.
Yeah, these are numerical simulations. We will be really very happy to have a quantum computer to run it, and we are exploring possibilities. I mean, the better chance will be in an ion trap because of having this all-to-all connectivity. Because and well, also maybe nearest neighbor with the connectivity of IBM, that is this heavy hex. I don't know. One will have to check, but of course, our desire will be to be able to run this in a quantum computer, of course, and this is why we did this study.
Yeah. Okay. Yeah. But I mean, if you can do that in this square lattice, is it very different if you go to a heavy hex because you also have?
Well, the heavy hex has less connectivity, and then I'm not sure. I mean, one will have to do the study and see under mitigation how it goes. I mean, the results in the end were not so different for the all-to-all to the nearest neighbor. So maybe also in the heavy hex will. I mean, yeah. Let's say that I'm not here for a chance.
So yes,
just a question. Like, it's just a curiosity though. Like, so you selected the error probability of your 2-qubit gates to be 10 to the -3.
Yeah.
Have you tried like higher values of that?
Well, I mean, if you try if the probability of error is higher, then I mean the results will be worse. But I think we didn't do a scan like.
I just saying because the state of the art in CNOTs, as far as I know, at least for Google, is like 10 to the -3.
Yeah. I mean, actually, it's not exactly this. I mean, there was some factoring what we tried that.
I mean, since you are putting Google, I imagine that maybe you were.
I mean, our simulations were not exactly for 10 to the -3. I think it was like something like 2 times 10 to the -3 or something. But I just put it because it's the order of magnitude. But I mean, it was looking that at least with the parameters of Google, it could work. And IBM is also getting much better there. Maybe the worst or the question to be explored is how the connectivity influences. But I think this type of algorithms, they are getting into the range that you can get a signal.
And so you think that if you scale it up to like 100 qubits in ion, like it would still.
Well, I mean, this was for the.
Yeah, I know. I'm saying.
I mean, if you go to this amount of, then I guess you will need error correction.
Okay.
I'm not sure. I think it's because these circuits, I mean, they are polynomial, but they are complicated. They are constructed out of these 3-body gates that, each of them, they can be decomposed in 2-body gates. No, the Toffoli contains 5 C nodes and then 1 qubit gates, and the control swap is just 2 C nodes and 1 Toffoli. So, but okay, the number of gates already for this particular case, these are the number of gates we have, and this is the depth. So the problem is that without error correction, if you go to much higher depth, then
Related to quantum error correction, so like we see that the depth is like you said it's linear somehow, right?
the depth here, no, I think it's going to be
Polynomial, sorry, polynomial.
polynomial. Yeah,
Yeah.
it's going to go.
Have you thought about how would this scale up when you have fault-tolerant gadgets? I don't know if I refer to that.
Well, I mean, yeah, in fault tolerant, in principle, if you are below threshold, you can do an arbitrary log. Well,
No, yeah, I know. I mean more like when you work with a fault-tolerant quantum computer, you need to decompose your unitaries into certain specific ones that you know how to do. Like
well, yeah. I mean,
the default should be some combination of these and
yeah. And I know that you can do transversally, and others ones it's just a mess with this. How is with the T gate that you have to inject and all this. Yeah, I
think it would be interesting, like for like...
No, of course, but I think that is more a separate problem. How to implement properly error correction for doing just not a memory for arbitrary computations. So I mean, there is a lot of activity on that, and I think it's extremely interesting. So in the moment, I think since this problem, for example, is close, I mean, has with errors not very far from what we have now, it can be reasonable. So even quantum error correction codes that are not too large, they could really make a big difference. So you don't need to go to something that can run for arbitrary depth, but with a reasonable small distance, you already can get a big gain for this type of problems. Yeah, of course, that will be very interesting to explore.
Okay.
Maybe
Yes.
just a small comment on the first part. You were trying to, if I understood correctly, you were trying to show this coordinate Bethe Ansatz equivalent, that it's equivalent in some MPS form to this algebraic Bethe Ansatz. And you were using some rules that could allow you to go from one to the other, right?
Yes.
So I was just going to comment that there's this tensor network language that's called ZX calculus. I don't know if you heard about it.
Yeah, this is one of the things I have heard, but I have not yet looked at it.
I mean, whenever you have to kind of invent rules to go from one state to another, it's typically a very ZXable problem. So you can, translate your states into ZX diagrams, and then with the rules that are sound, are complete, you can go from one to the other pretty much, by clicking a button in some software or just doing it manually even. And especially if it's analytic, I mean, the fact that you can do it without ZX, it already like, it's very suspicious that, I mean, it already tells me that it's very likely that you could do it in ZX very easily.
It's possible, but I don't know. I only know the analytic expression starting from the coordinate Bethe. Well, no, okay, it's true. I will know. Yeah, I will have to. I don't know. I confess I have heard about the CX calculus, but I have not explored. And there, I think the nice result was, I mean, that the relation between these two formulation is this very deep structure in integrability, that is this non-local change of basis in the auxiliary space. And this was something that maybe was hinted like in in this paper, but it was not really stated. And even this sort of this invariance and the permutation was also not clearly stated.
Yeah.
So maybe this other language can also help. But I think from the point of view of the theory of integrable systems, I consider this a nice result.
Yeah, but I'm sure you could like.
I agree. I mean, it will be nice to look at it. But
it also has the benefit that it's like a formal language, and that, whatever you write as an equivalence is actually a correct equivalence rather than.
Okay, so maybe you can tell me a bit more about this ZX calculus that it's
relatively simple.
Okay.
Okay, so I think we can close now the session. So thank you very much again, Esperanza.